Okay, so in the synchronous session this week, we are going to precisely calculate this maximum efficiency, or rather the efficiency of a reversible thermal engine cycle. And to do that, because of Carnot theorem, we can simply choose the cycle that is simplest for us to work with and the working substance that makes the calculation easier. Now, of course, we are going to choose the simplest system, single component expansive system, and we are going to run a Carnot cycle with this when the gas in the expansive system is in the ideal gas limit. Okay, so in that case, you obtain an expression for the maximum efficiency. So it's important to remark is that if you were working with any different substance, with any different equation of state, and any different cycle which effectively operates between two well-defined temperature levels, that's has to be fixed. No matter how complicated your expressions are, your calculation will in the end simplify to this very simple neat expression, which is because of Carnot's theorem. Okay, so remember that this is calculated as 1 minus, and then here is the heat rejected, in this case divided by the heat absorbed if you are running a heat engine. Okay, good. So, okay, one thing to highlight about this very simple expression that we got is that, well, you can see, right, so that the ratio of the heats exchanged with either heat bath simply equals the ratio of the temperatures of these baths. Okay, and this relationship is actually a definition of what the true thermodynamic temperature is. So remember that up to now, for us, the true thermodynamic temperature was just the empirical temperature that you can measure with a gas thermometer at constant volume. And when you express that temperature in the Kelvin scale, which was some scale that we had introduced, that seemed as arbitrary as the centigrade scale or the Fahrenheit scale or any other temperature scale. But now here we see that the second law of thermodynamics, which is equivalent to Carnot's theorem, you can think of Carnot's theorem as a statement of the second law, if you like, it singles out this specific temperature scale that we're using. Okay, so we get precisely not just any function of the temperatures measured in the Kelvin scale, we get actually the ratio of those temperatures without any prefactors, without any added terms, just the ratio of the absolute temperatures. And like I say, this is a way to define the temperature scale. So imagine, for instance, that operationally, okay, this is not something that you would do in practice, but imagine that you want to, say, measure the temperature of the cold bath and you know the temperature of the hot bath. What you can do is you can try to run a reversible heat engine cycle, and then you would measure the heat exchange with either heat baths, take the ratio of that, and from this expression you get the unknown temperature. Okay, so that would be an operational, at least formal way to define the absolute thermodynamic temperature scale. So this was one thing that our theory was missing, and this concludes this chapter about thermal engines. Next chapter is a self-study pack about what happens with real engines. So not engines that run in idealized quasi-static, say infinitely slow cycle times, infinite cycle times, but real engines that run in finite time. And the following chapter is actually going to be the last in the first part or block of the subject, which is basic thermodynamics. And this chapter is going to be about entropy. So this is the last element of the theory that we need before we can actually use it for something practical and useful and study real gases, phase transitions, and so on. So I will see you in the next chapter.